Hello everyone. In this video we are going to talk about the stability margins, the gain margin and phase margin in particular. In practice, usually we have the open loop transfer function LOS for a given system being strictly proper. Okay, so it's usually the case. In most of the cases, LOS is strictly proper. And then when this is the case, the amplitude of L of j omega will go towards 0 for omega approaching the infinity. This happens because the number of the order of the denominator will be bigger than the order of the numerator, and then as omega approaches infinity, there will be omegas remaining at the denominator, and as a result the amplitude will go towards 0. We also assume that the generalized gain L tilde of L of S is positive. I hope you remember what the generalized gain is for different types of the system. And we assume that L, the open loop system, has no pose in the right half plane. The open loop system is stable, so it also means that we have, if you refer to the Nyquist criteria, since there are no poles in the right half plane, P will be equal to 0. And as a result, N equal to 0 means that Z is also equal to 0. So P equal to 0 means that the open loop system is stable. And now in order to have closed loop system stable, we need to have N equal to 0. And N equal to 0 means that the Nyquist plot should not encircle the point -1 on the real axis. We also assume that the phase of L of j omega becomes equal to -180 degrees for at most one value of omega bigger than 0. Then the gain margin, which we also denote as GM, gain margin, is the factor by which the generalized gain can be raised before instability results. And this will happen because we have assumed that the Nyquist plot initially by setting k equal to 1 doesn't encircle the point -1. Now, if we continue to increase the gain of the system, the generalized gain L tilde or K, at some point, the point -1 might be encircled, and as a result, the system will become unstable. The amount of the increment that we can have for the gain before the system becomes unstable is called as the gain margin. We can read the value for gain margin directly from the Bode plot, and it will be the distance between the amplitude of L curve and the amplitude of L of j omega being equal to 1 line at the frequency where the phase becomes equal to -180 degrees. So basically, in the amplitude plot that we have for L of j omega, we will check the frequency at which the phase of L of j omega becomes -180 degrees. If it happens, let's say we have this as an example. So at the given frequency, which is for this example will be this frequency omega star, we will find out that frequency omega star. Then we will check the amplitude plot. We will find the distance between the amplitude of L of j omega at that frequency, which is here, and the 0 dB, or where amplitude is equal to 1. And this will give us the gain margin. So with using the Bode plot, we can determine the gain margin. Gain margin is a factor by which the gain can be increased. Therefore, if gain margin is smaller than 1, or if it's smaller than 0 dB, it indicates that the closed loop system is unstable. But if gain margin is bigger than 1, it means that the system is stable. The closed loop system is stable. We can also refer to the root locus plot in order to determine the gain margin. In that case, the gain margin could be identified as L tilde cross over L tilde norm. L tilde norm will be the nominal generalized gain, and L tilde cross will be the generalized gain at the point in which we have the root locus branches crossing the real axis, the imaginary axis, sorry. Let me give you an example. Let's assume that we have these 3 poles. If I draw the root locus for this system, it will be almost like this. Now, for the system, if we want to determine the gain margin, we need to find out the L tilde nominal over L tilde cross. And let's say that we have GP of S in the form of 1 over S plus 1 times S plus 2 times S plus 3. And now you can see the generalized gain for this case. It's a type 0 system, so L tilde, which is indeed limit of L of S as S goes towards 0 for the system, will be equal to 1 over 6. Assuming that GC is equal to K and it's equal to 1 at this point for the nominal value. So this is LT nominal. L tilde cross, on the other hand, will be the value that we have here for the generalized gain, and it will be equal to limit of L of S as S goes towards 0, and it will be equal to some K star, which is what we have here. We can assume that it is equal to 5, for example. Okay, we can find the exact value. So it will be K star times GP of S as S goes towards 0, and it will be equal to K star over 6. Now, if we plug these values, we will get K star over 6, 1 over 6, and we will obtain K star. And you can see that K star is the amount of the amplification of the gain that we can have before the system becomes unstable. If we increase the gain more than K star, the system will become unstable with 2 unstable poles. And before that, the system remains stable. So in these 2 ways, we can determine the gain margin. You can see an example over here. We have a system for which the Bode plot is shown. And here we have a part of the Nyquist plot. At low frequencies, the amplitude is huge. When frequency approaches 0, amplitude approaches the infinity. Then the amplitude decreases and decreases, and at the end, when frequency goes towards infinity, it becomes 0. And you can see it over here as well. Yeah? In terms of the phase, the initial phase is around minus 90 degrees, and as omega increases, it reaches minus 180, and at infinity, it will reach minus 270 degrees. So looking at the Bode plot, we need to identify the frequency in which the phase becomes minus 180, and that is this frequency over here. And then omega equal to 1, yeah? And then we go to the amplitude plot. We find this frequency here. And then the difference between the 0 dB, here we have 0 dB, and the amplitude at that frequency will give us the gain margin. In this case, the gain margin for us is equal to 6 decibel. So this difference is 6 dB for us. I will talk about the phase margin in the next slide, and then we'll come back over here. Yeah. If now we look at the part of the Nyquist plot that we have here, the graph is shown considering k equal to 1. Now, if we increase the value of k, this graph will be inflated. And at some point, it will cross the point -1. If we continue to increase, it will include the point -1 inside, and as a result, the system will become unstable. But right at the point in which the graph crosses the point -1, we can find out the gain margin, because this is the indeed that is when the system becomes unstable. Yeah. So over here we have k equal to 1, and here we have indeed k equal to gain margin. Yeah, that's the amount of the increment. But now we see that the amplitude when the phase is equal to -180 is here. Yeah, here we have the amplitude. If I call it A, and then we multiply A with the gain margin, we will obtain the amplitude equal to 1. And as a result, A will be equal to 1 over gain margin, or gain margin will be equal to 1 over A. You can take both into account. So looking at the Nyquist diagram, you can determine the value for the gain margin by finding out this value. So A will be equal to 1 over gain margin, or gain margin will be equal to 1 over A. And you can determine it by referring to the Nyquist graph. On the other hand, if we assume for simplicity that the amplitude of L of j omega becomes equal to 1 for only one value of omega bigger than 0, then we will be able to define the phase margin, or PM. The phase margin will be amount by which the phase of L of j omega exceeds -180 degrees when the amplitude is equal to 1. If phase margin is smaller than 0 degrees, it means that the closed loop system is unstable. If phase margin is bigger than 0, it means that the closed loop system is stable. We can see it over here. Yeah. If you look at this example that we have here, for the Bode plot, in order to determine the phase margin, we find out the frequency at which the amplitude becomes equal to 1. So it's this frequency, because the amplitude is equal to 1 over there. And then we move to the phase plot. And at the same frequency, which is here, we find the difference between the phase of the L of j omega at that frequency and -180. For this example, it's equal to 22 degrees. And since it's a positive value, it means that the system is stable. We can also determine it by referring to the Nyquist plot. To do that, we need to draw a circle with the radius of 1 and the center at the origin. And then the phase margin that we are going to find will be obtained by finding the phase difference between the point in which the amplitude becomes equal to 1, finding the phase over there, and the difference between that point and the horizontal line that we have here will give us the phase margin. So it will be equal to indeed 180 degrees. plus the phase of L of j omega, where amplitude is equal to 1, at a frequency in which the amplitude is equal to 1. We refer to that frequency, amplitude of L of j omega equal to 1. The frequency over there is called the crossover frequency, or to be more specific, it is called gain crossover frequency. Sometimes to the frequency in which the phase becomes minus 180 degrees, we refer as the phase crossover frequency. So in that way, we can determine the phase margin. Larger values of gain margin and phase margin will lead to more robustly stable closed-loop systems. So basically, we usually desire bigger values for gain margin and phase margin. If the system parameters in this case are slightly changing, the closed-loop system will still remain stable if we have a big gain margin and phase margin. Now, having all this in mind, we will have the Bode criterion for the stability, which is a simplified version of the Nyquist criterion. Having all the assumptions in mind, if we assume that L is strictly proper, L tilde is bigger than 0, the generalized gain, P is equal to 0, meaning that the open loop system is stable, and L of j omega is equal to 1 for only one value of omega bigger than 0, then if phase margin is bigger than 0 degrees, the closed-loop system will be bistable. If it's smaller than 0, the closed-loop system will be unstable. In the next videos, we will go through two examples in which we will find the gain margin and phase margin and determine the stability of the system referring to these stability criteria. That's all for this video. Thank you for watching and see you in the next video.